Hey guys, today we're going to be learning about a very important concept in computer science, recursion. Okay, I'll level with you guys. When you first start recursion, it's confusing as hell. But once you kind of get used to it, it becomes a fundamental tool in your toolbox when programming. It really actually helps shape the way you think about designing algorithms. All of the functions I've been showing you so far have been defined in terms of other functions, even if that function was just like plus or something like that. Remember way back to our first tutorial, I defined a function factorial that took a int n and gave back the mathematical factorial of that int, which is basically whatever n is, you multiply n by n minus 1 and then n minus 2 and so on and so on and so forth up until 1. So one way we could define this is in terms of the product function that takes a list and multiplies everything in that list. And then we use this sort of list generation syntax to make the list of 1 to n. If we were to consider how that function was evaluated, we first remember that everything is evaluated like a expression, and we move through a stepwise process of evaluating whatever has the most precedence first. So factorial 4 is defined as the product of the list of 1 dot dot 4. So one of the first things we would do is we would expand this list to be 1, 2, 3, 4. And then we would take the product of that list, which would basically just insert multiplications between every element, and then we would evaluate that arithmetic to 24. What makes a function recursive is that it's going to be defined in terms of itself. So it's going to call itself inside of its own definition. For example, that factorial function that we just defined using the product function, the prelude, what if we wanted to find it more directly ourselves? We could define it by first pattern matching on the input. And we say, well, the factorial of 0 is 1. And we just kind of hope that we never call the factorial of a negative number just because it doesn't make sense. And if it isn't 0, then it's some n. And what it's going to be is n times the factorial of n minus 1. Okay? So this function is going to get called again each time, making n smaller, okay, by 1 until it gets to 0. Let's look at how the evaluation for the recursive definition works. So let's say we start at factorial of 3. What we do is we replace, this, we can look at it this way. Which pattern does it match? It matches this one here, okay? So then we replace this left-hand side with this right-hand side, subbing in 3 for n. So the factorial of 3 is going to become 3 times the factorial of n minus 1, which we'll just do that arithmetic on the spot, is going to be 2. Then what's going to happen? Well, factorial is going to get called again. So once again, we pattern match, and we realize, oh, okay, it matches this pattern, and we do the same thing. We end up with another multiplication. So this becomes 2 times the factorial of 1. And then, of course, we evaluate that again. It becomes 1 times the factorial of 0. And now we're at what we would call our base case. So now when we go to our pattern matching, it pattern match to this step here. So this would be our base case. And we just returned 1 now. And now we can evaluate all of that arithmetic. Let's try another example. Let's say we want to create a function pal that takes a integer m and computes its power to n, okay? So this will compute the power, I'll put this in a comment about m to the power of n. Okay, this actually already exists in Haskell, but let's redefine it. So pal of m to n is going to equal, so what we're basically going to want to do is we're going to want to multiply m n times, okay? So a good place to start is m times something, okay? So we're going to have to multiply m n different times. So what we're going to do is we're going to call the pal function again n minus 1 times. So we consider this is the nth time that we're calling the pal function, and in order to complete this, we're going to call it n minus 1 times. Okay? So the way it is right now, let's say we just load this into GHCI. Let's open up a terminal. Back GHCI, source, .hs. Okay, and let's run how, let's say 2 to the power of 4. Uh-oh. Okay, so we got an error here. Exception stack overflow. So what happened here? Well, we called POW. So let's try and do the evaluation in our heads. We'll write it in a comment. So we'll use this curly braces and a dash to make a multi-line comment. Anything that we have inside here, it doesn't matter. Okay, the compiler just completely ignores it. So let's say we called power 2 4. Okay, what is this going to evaluate to? So let's sub in this left hand side for this right hand side. So this is going to be m, okay, so there's 2 here, times power, we just call m again, and now n minus 1. So this is going to be 4 minus 1, which of course is 3, right? So what is this going to evaluate to? Well, this is going to be 3, of course, right? But then what is this going to evaluate to? Well, we'll leave this alone for now. What's left to evaluate? We need to evaluate this again, right? So let's now sub this one in, okay? This side here, where m is now 2, and n is now 3. Let's sub this in. It'll be 2 times, and what we'll do is we'll put brackets around to specify, oh, everything inside here is going to have to be evaluated first. So every time you make a function call, it's going to have precedence inside of it, right? So now this is going to be 2 times pow 2 3 minus 1. Okay, and you're going to see right now, well, it's just going to keep doing this. You're just going to keep calling pow over and over and over again. It's never going to stop. All right. What we wanted to do is we want to create some sort of base case. So what we'll do is we'll put above, and make sure we have to put it above pow m0. Okay. You do have to make sure that this is above this, because if we put this below, well, it'll never match to 0 because n would already match to 0. N could be anything, right? If we put pow m0 underneath here, it'll go in order and be like, which one can I match to? And even when you call pow with n is equal to 0, n will still match it. So it'll never end up getting down here. So make sure to put it on top. And we'll put pow m0 is equal to, and, call back to your math class days. What is the power of anything to 0? It's 1. Okay, so this is our base case, and this is our recursive case, we could say. Okay. So now this is going to keep evaluating. So we can just keep going here. And this is going to go to 2 times pow times 2 minus 1. Okay. And this is going to be 2 times pow 2. And this is actually going to be 0 at this point. So this was 2 minus 1. So now this is going to be 1 minus 1, which is, of course, 0. So now we're at our base case here. So now we're going to write, okay, so now we sub this side for this side. So this is just 1. So now we're actually able to stop. And then we can evaluate all of this. Which ends up being 16. Just like how we could define recursive functions, we could define recursive types as well. So take the following data type nat. The point of this data type is basically to rebuild the idea of a natural number. So a natural number inside mathematics is any positive whole number. So we can define a natural number as being either 0 or the successor of another natural number. So the idea is the successor would be like +1 of another natural number. So this nat type is going to have two constructors, 0 and successor. So using this definition, we're able to define a data type that actually has an infinite amount of values associated with it. So the first value would be 0. We could call that the base case of this data type. And then we would have the successor of 0, and then the successor of the successor of 0, and just so on and so on and so on into infinity. Let's take a closer look at this data type because it really is a very interesting data type. It essentially shows how you can just symbolically and very formally define how a number works. So we're going to have 0 or the successor of nat. So I can define 1 is equal to the successor of 0. Well, I could have started at 0, I guess. 0 is equal to 0, obviously. And 2 is equal to the successor of the successor of 0. Or I could just write 1 here, right? I just defined that. 3. And I could just keep counting like this, right? I'll just write this one full out just to emphasize what's going on. So I can define just an infinite amount of given values given this definition, okay, that I can use to count up to infinity. Say I wanted to define some functions for working with these. Let's say I could define a function nat to int that would take a nat and return an int. Okay, so what I would most likely do here is I would pattern match on the two values. So I would have the nat to int 0 is going to equal to something, and nat to int the successor of n is going to equal to something. So I'm going to have to use recursion because this is a recursive type with possibly infinite values in order to turn this into, oh, and I misspelled this here. In order to turn this into an integer, okay, I'm going to have to recurse as well. So I'll say that every time I have a successor here, what is this successor like representing here? Well, like I said before, it's representing incrementing by 1, adding 1. So I could say this is 1 plus nat to int n, okay? So I have the successor of n is the same as 1 plus whatever the integer of n is. And I would keep doing that until I got to 0, and, you know, what's the integer corresponding to 0? Well, just 0, right? Similarly, if I wanted to go the other way, I could define a function int to nat. Okay, we're going to take an int, and we return a natural number, and this is going to look basically the same. So int to nat 0 is going to equal 0. I'm just going to kind of like flip things around. Int to nat x is going to equal, and what I'll do is I'll take the successor of int to nat x minus 1, okay? So I can load these into GHCI now and play around with them a little bit. So I'll save stack GHCI. Whoops. Okay, so I could I can do int to nat. Let's look at the nat that corresponds to 10. Oh, and if I want to show this, now is a good time to point this out. Whenever I make my own data type, if I want GHCI to be able to show me what that data type looks like, I have to write deriving show underneath. This is a little weird thing. We could talk about this later when we go over type classes, but just to give you a little bit of an idea of what's going on here, there's something called the show type class that will turn things into strings for you. And in order for GHCI to actually like print something out, it needs to turn it into a string first. So anything that prints out needs to be part of this show class. And this deriving thing is an interesting mechanism that Haskell has that basically just means like, yo, make an instance of the show class for me and just do it the way that you probably think I want to do it, right? In some generic way, we would call it. So put this here, make sure to save and reload. And now we can do into nat10. Okay, and now it's able to show what the natural number will look like. There's a lot of brackets going on here, right? Now here's an interesting thing to do. We can take into nat10 and do nat to int on that and just see if it turns it back to 10. Hopefully it should if we defined it correctly. It did. So pretty neat. We could move back and forth now between our own data type for counting stuff and the natural numbers. And this would actually be very useful if you had some function that at some point you wanted to make sure all of the arithmetic was positive. You didn't want to deal with any possibility that you could end up with a negative number. Let's go even further with this now. And let's define a function add to add two natural numbers together. So there's two ways we could go about this. So the kind of cheat that we came up with now, so add is going to take a natural number and another natural number, return another natural number. It's going to take an m and an n, and what we can kind of do is we could just take advantage of the fact that we could convert the natural number to an int, and then we can just add them together using the integer addition that's already defined for us. And then we just convert it back. This is kind of a bit of a super hacky solution. For one thing, it's int to nat. For one thing, it's very inefficient. Okay, the way we would have to go about this. If we looked at it this way, depending on, let's say, however big a natural number we have, it's going to take n evaluation. So n subbing a new function in, like n recursive calls for a natural number of size n, okay, to convert it. So it's going to take n calls, and then another n calls to transform it back. The better way we can go about this is let's pattern match on the first argument. Now let's start off with the base case of if the first argument is 0 and we're adding some n to it, it's just going to be n. 0 plus anything is just going to be n. On the other hand, if we have the successor of some natural number m and n, then the addition of this is going to be the successor of add m and n. Okay, so the idea here is that we're kind of just rebuilding the natural number. Okay, we're going through this natural number and we're rebuilding it. So for every, let's say we have, you can look at it this way. Let's say we have some natural number, the successor of the successor of 0, and we're adding it, we're writing an infix notation with the successor of 0. What's going to happen? What we're doing is we're taking the left one and we're just gradually piling on the successor from this side onto the successor of this side. So this is going to become the successor of 0 added to the successor of the successor of 0. And then we're going to pile on this successor now. I'll put this all in comments here so that you guys just know. This is the code I'm writing that should be included. So then this is going to be equal to 0 add the successor of the successor of the successor of 0. And then what do we do? So, well, now when this is 0, then we just return this side. So then we just delete this, okay? And we just end up with the successor of 0. So now that we've seen an example of how we could very formally define how a number is represented as like a data type, like how it is built, how it is structured, and how operations like addition are structured over those numbers, let's just talk about how arithmetic expressions are structured in general. So consider the expression 1 plus 2 times 3. We consider this expression, its structure, to be kind of like a tree that I'm showing here on the right hand side, where the leaves are values and nodes are plus and multiplication, all these different operations. So using recursion, we can make a data type. This is going to be a tree-like data type. We'll talk about trees a bit more later, to represent these expressions. So we call our data type, we call it EXPR, short form for expression. And it's either going to be a value, okay, and right now we'll limit our expressions to be ints, okay? We'll have expressions that have a bunch of different ints, and we'll limit ourselves to 2 different operations. So an expression is either going to be a value, or it's going to be the addition of 2 other expressions, or it's going to be the multiplication of 2 other expressions. So for example, we can use this data type to encode this previous expression, this 1 plus 2 times 3, okay, with the following value. So what we have, we'll start at the top of this tree. So the first operation is plus, and then the left of that plus is 1. So we're going to have add, and the first expression here that add takes is just going to be val1. And the second expression that add takes is going to be this multiplication here, okay? So this whole other expression, multiply, okay, and then multiply itself takes 2 expressions. So the expression on the left-hand side is going to be 2, and on the right-hand side, it's going to be the value 3. Let's explore this expression type in VS Code for a little bit. So before I get into it, I want to be ultra specific about what we're trying to do here by creating an expression data structure. So say we have some expressions that we want to be able to represent, like anything's like 2 times 5 plus 6, right? Let's say you're creating a program that's like a calculator program, and you want the user to be able to enter in an expression, and then you're gonna compute the value of that expression, but you want to be able to like store it. Maybe you're gonna not compute it at once. Maybe you're gonna want to be able to put expressions together. You're gonna want to be able to manipulate them. You might be tempted, like I would say a novice programmer might do something like this, where they have the user input the expression, and they just keep the expression in like a string, like 2 times 5 plus 6. And then when they write code to evaluate it, what they would essentially do is they would go through and they would iterate through this string and see like a times, and then try to write some code to multiply things together. It'd be very messy, okay? What I'm saying is the preferable way to represent an expression would be to put it into a data structure like this. So you might have it set up where the user would input the string at first, like they would give you input and you would take it as a string, but then you would immediately convert this string into a data type like this. And then you would have this data type that you could manipulate, say, evaluate the expression to a result or something more directly. So let's write a function to do just what I was talking about. Evaluate the expression. So this is a function, eval is going to take an expression and so you're going to return an int val. Okay, and you're going to see that this function is going to be way easier to write. Okay, much nicer to write than if we were taking a string like this as input instead of the expression data type as input. So let's write eval val of n. So we're going to pattern match on all the different possible values of an expression. So if we have a val of some type n, the way we're going to convert that to an int is we're just going to return that n, not 1, whatever n is here. Okay, so val here is just kind of like a box that we're keeping the int in to let it know that, oh, this is of type expression. And once we want to convert it into an int, we just kind of take it out of that box. Now, the more complicated scenario is when we have add, let's say, x, y. Okay, we're adding 2 expressions here. So what we're going to want to do is convert x into an int and then add it. So we want to be able to say x plus y. So we can't do this right now. Like, let's say I just write x plus y like this. And I look at the type error and it's saying, well, you can't do this because plus wants an int. But x isn't an int. What is x? X is an expression. Well, how do we turn an expression into an int? Well, that's what we're doing right now. We're writing the function. So what are we going to do? We're going to use recursion. Eval x and eval y. So we convert x and y into integers, and then we just add them together. Now let's move on. The final one, mult xy. And guess what? This is going to be basically the same thing, except now we multiply the two numbers together. So if we load this now into GHCI, so if we save and load, we go around and we could start evaluating some expressions. So what would this expression be? Let's actually look at this here. So let's say we wanted to have 2 times 5 plus 6. So in expression format, encoded as our expression data type, this is going to be add mult val2 val5 to val6. Okay, I'm going to add these things. So let's reload. Let's try evaluating that. Let's eval expression. Okay, and this evaluates to 16. Is that right? 2 times 5, 10 plus 6? Yep, seems about right to me. So the example of the expression data type that I showed you is a more specific example of a more generalized data type that's used all over the place in computer science, a binary tree. So this is a data structure that's composed of nodes and branches between these nodes, okay? And every node has 2 branches or no branches at all. And the nodes with no branches at all are called leaves. So for example, in this binary tree here, 5, 3, and 7 would be nodes. They each have 2 branches, and 1, 4, 6, 9 would be the leaves. So the way we're going to define the tree structure is going to be very similar, and we should make note to the expression structure. So the tree structure is going to be equal to a leaf int, and so here's going to be the main difference. So let's make an example of an expression tree in our comments here. So let's say we have an expression. So each of the nodes is going to be either a multiplication or a plus. Okay, because we decided to make the values specifically say add or multiply. We decided to make them specifically represent that. Okay, whereas with a tree, we're going to be more general. So instead of having the nodes be specific things, the nodes themselves are just going to be integers as well. So a tree structure is going to be like, whatever, 5, 4, 3, 2, 1. Okay, so here's going to be our tree structure. So what I'm going to do is I'm going to have a leaf, which is going to be the same thing as val, but then instead of having different nodes, I'm just going to have one node, and it's going to have an int attached to it, and 2 trees. Okay. So we could define, let's say, write a value for our tree. Tree equals node, and so let's remake this tree in our data structure. So this is going to be node 5, and then the left of it is going to be a leaf 4. Leaf 4. Oh, this isn't right. Okay, so it's going to be a leaf 4, and then the right is going to be another tree with a node 3, leaf 2, leaf 1. Okay, so here's our example tree. And we can define some interesting functions on this tree. So let's say we want to define a function occurs. And what occurs is going to do is it's going to take an int and a tree, and it's going to tell you with true or false if that integer exists anywhere inside of this given tree. So the int, we'll just call it m, and we'll have a leaf n. So we're going to pattern match on the 2 cases of the tree. So the first one, the easy one, is going to be the base case here, the leaf n. Okay, and we're just going to say, well, is m equal to n? Okay. The other scenario is going to be a bit more complicated. So we're going to have a node n and 2 other trees, t1 and t2, we'll say. And again, we'll just ask, well, is m equal to n? But now we have to check, well, it's not just if m is equal to n, is m also inside t1, or is m also inside t2? So we need a way to be like, well, does m occur in t1? Well, we have a way, we're defining it right now. So we're going to use recursion. So we're going to have to call occurs on t1 and occurs on t2. Now we're going to need some way to put this all together. So for that, we're going to use the binary operator, this double bar, which means or. Okay, so this is a logical or. So I could show you. Oh, and we're going to have to say occurs m t1, occurs m in t2. Okay, so if we load this into GHCI, let's do stack GHCI source yield.fs. So the way or works is true or true is going to equal true. True or false is going to equal true. False or false is going to equal false. False or true is going to equal true. So basically, the only time that or ends up being false is if both things are false. So the reason it's perfect for this scenario is as long as m is somewhere inside of this tree, we're good. So we're basically saying like either this is true or this is true or this is true. As long as one of these things is true, then we can return true. But if we get through the whole thing and it's just always false, then it's going to return false. Then it's not inside of the tree. So let's give this a try. We could say occurs 1 in tree. Okay, using that tree variable that we defined. True. Let's try a negative. So occurs 7 in tree. False. There we go. It works. Now let's try another function. Let's say we want to take a tree and we want to turn it into a list. So the idea is that we could take this tree and we could like kind of like sandwich it down into being 4, 5, 3. All right, I guess it's actually 2, 3, 1. Okay, we just kind of take this tree and we'll flatten it down. Okay, so we could write that function. We'll call it flatten. And what it'll do is it'll take a tree and it'll return a list of int. So just the list of the tree's values. So how are we going to write this function? So I'll give you a hint. We're going to have to pattern match for it first, just like we did with occurs. Okay, so we're going to have flatten the two scenarios, leaf n is going to be equal to something, and flatten node. And so there's n, t1, t2. And okay, we could probably guess that, yeah, you're going to have to use recursion again. So let's start with this case first, the base case, because this is often easier to find. So what is, if we were to just flatten a leaf, like let's say the tree was only 2 and we wanted to flatten that, what would that be? It'd just be the list of 2, right? So let's just put the list of n. Okay, that's pretty straightforward. Now, how do we flatten this tree? So, well, first of all, in order to flatten this node, we need to first flatten T1. So we need some way of flattening this tree. You guessed it, we have it. We're currently defining it. So it's called flatten T1. Okay, and then we're going to have the list of n, and then we're going to have flatten T2. And we're going to need some way to put this all together. Okay, so this is a list. This is going to be a list. So remember, this returns a list here, a list of n. And this is going to be a list. So we need some operation, some operator that puts lists together, that takes 2 lists and puts them together. So thankfully, the prelude gives us one. It's called plus plus. So we're just going to put, I'm actually going to write it this way, just like we did with the last function. Plus plus, plus plus. Okay, so this is actually very, very similarly written to occurs. And you'll notice that there's kind of this pattern going on in terms of how we think about writing these algorithms over these data structures. The first thing we do is we pattern match on them. And there's always going to be kind of like a base case and a recursive case. Base case, recursive case. And then we do what we're setting out to do in like a very, so in the base case, there's always like the simple case, right? Of like just throw it into the list. Yeah, just do the comparison. And in the recursive case, we do that too, but then we put it together with calling the recursion. And there's always going to be some different way of putting it together. In this instance, it was using the plus plus operator because we're returning lists and we need to put the list together. In this case, we were returning a bool value, so it's the OR operator, so we put those together. But there's always some way of putting them together. So this is just an interesting thing you should make note of, that it's a style of thinking. Once you get used to this style of thinking, of writing algorithms in this style, then writing more complicated algorithms that use recursion is going to seem very easy, as opposed to where you're starting out right now. Okay, let's talk about one more example. Is there any scenario, let's go back to this occurs function. Is there any scenario where this occurs function could be made more efficient? So first of all, I'll point out the fact that in order for this occurs function to evaluate, what essentially it has to do is it needs to check every single node and leaf in this tree. So there's no scenario, let's say the tree has n things inside of it, it's making n comparisons. So it asks n times if this is equal to this, if there's n different things in this tree. So is there any way we can cut down those number of comparisons? Well, not unless we make some sort of restrictions on what kind of tree we have here. So one thing we could do is we could say, do you know what? I'm only going to accept trees that are ordered. So I'm only going to accept trees. I'm just gonna write an algorithm that assumes that the tree that's given to me is in a certain order. So let's rearrange this tree to make it ordered. So what I would do is I would make this into 3, basically reverse this tree. 2, this would be 4, and then this would be 5. Let's get rid of these things. So this is an example of an ordered tree. And there's actually a particular name for trees that are ordered like this. They're called search trees. They're called search trees because if we flatten this, it'll end up in an ordered list, okay? If we were to flatten this tree using our flatten function from before. Oh, I actually made a little error here. 2, 3, 2, 3, 4, 5. I would end up with an ordered list here. And they're called search trees, I should say, because they're easy to search. So now we can rewrite our occurs function. Okay. And the way we're going to rewrite it is we're not just going to do the comparison here. We're going to say, let's actually use guards to do this. So let's have some guards here, and we'll say if m is equal to n, then true. But we're going to make another comparison here. If m is smaller than n, okay, so if m is smaller than n, then that means we only have to check the left tree. So we only have to do this, occurs m t1. Whereas if m is bigger than n, then it's occurs m t2. So this way, okay, note it's only going to work if the tree is sorted, okay? But if we know that the tree is sorted, that's a search tree like this one, this way we potentially cut down on doing a lot of work, okay? Because we're not always searching both trees, okay? If we were to look at how occurs would, let's say we called occurs 2, okay, on the tree from before. Okay, what it would essentially end up doing is it would look at 4 and it would say, here, I'll move this up here. Okay, it's going to look at 4. It's going to say, is 2 equal to 4? Nope, it's going to move on to the next one. Is 2 smaller than 4? Yes, it is. And it's going to move down here. And it's going to say, is 2 equal to 4? Or is 2 equal to 2 now? Sorry. It's going to say, yes, it is. That's true. So I guess it would be more interesting if I put 1 here. But then obviously it would just move down this left side. It would go from 4 to 2 to 1. And it would never have to do any evaluation of this side of the tree. So you can imagine if this side of the tree was much bigger, if we had a much bigger tree, we would end up saving a lot of computation. In fact, the amount of computation has to do with something called log time. We would say that this is O log 2 of n. But we'll talk more about that later. This is it for this week, guys. I hope it was enough content for you. Take it easy.